Hello everyone and welcome back to Nunley Math. I'm your host Aaron Nunley. Thank you so much for joining me here today as we look at the fourth in our series of videos on graphs of functions. We have already talked about the linear function. We've already talked about the quadratic function. We've already talked about the absolute value function, and today I'm going to give you one more. Here's our new type of function. F of x equals x to the third power minus 2. Now, just like in our previous videos, our goal here is to get a sample of what this will look like so that we can begin to look for patterns that can help us to graph these more quickly in the future. Having said that, that means that when we do this today, we're going to do it the easiest way possible, which is sticking in random values for x, putting them into our function, seeing if they work and seeing what they give us. Then we're going to graph those and look at the at whatever happens to show up. This is the longest, slowest, most tedious way to do this, but it is the easiest to understand. Hopefully, we would never have to do this entire process again. So let's walk through it together. We're going to look for some key characteristics and then see if we can tie this all together. I'm going to stick in a 0. I like to start with 0 most of the time because 0 is in the center of the coordinate plane that I've given you, and it tends to give me numbers that tend to fit within this space. It's also fairly easy to compute. Just like always, the domain that I chose, 0, goes into rule F. The rule says whatever you stick in here, you're going to cube it and subtract 2. So 0 cubed minus 2 gives me negative 2. And you get 0, negative 2, which then you plot on the coordinate plane. I would suggest that you pause the video and plot these on your own before checking to see if yours matches mine. I'm going to do this much more quickly now because this is the fourth video of this type we've done, and by now you should be getting pretty good at it. If I stick in a 1 into my rule, the rule is cube it and subtract 2. That gives me negative 1. If I stick in a 2, I get a 6. I graph that. If I stick in a 3, I get a 25. Now, if you look at the space that I've given you, 325 does not fit. 311 is the highest I can go. But it's still an important point because it tells me that I'm going to go out of this space somewhere between the 2 and the 3 because 2 fits nicely in the space, 3 is way above. So I'm going to put a dot just to kind of guide me when I'm connecting my dots because I know that eventually this has got to go up to 3. Now I've got a nice curve that I can connect here in just a second, and it guides me where I need to go. Also, by the way, if you stick in a 4, you would get 462, and so I know that way up here, eventually this is going to go over to 4. It makes sense that this should grow pretty quickly because anytime you cube something, you're turning into fairly large numbers. Let's see what happens if I go the other direction. If I put in a negative 1, I get negative 3. If I put in a negative 2, I get negative 10. And if I put in a negative 3, I get negative 29. Once again, negative 329 is way off my graph, but I do know that I'm going to go out somewhere in here between 2 and 3, probably closer to the 2, and so I just kind of estimate where that goes. And it gives me a nice little path for me to connect my dots. Do you notice anything interesting about this? As I graph this, let's see if I can do this by hand. My graph seems to go, this is really hard with a mouse, I'm sorry about this, I'm going to do the very best I can. My graph seems to start off growing really quickly here, and over here it's growing less quickly, and then down here it's actually growing even less quickly. Now we can pick some values in between 0 and 1, or 0 and negative 1 to even this out just a little bit. I'm not going to make you do that today, but just know that this is not a straight line between these two, but it's actually a curve. And that curve continues kind of like this. Again, if I had a pencil and paper, this would be a lot easier to do, but for our purposes for now, this seems to work out pretty well. So it looks like starting at this point, I grow, then I grow faster, and then we started growing really fast. We had a growth from, what, negative 2 to negative 1, negative 1 to 6, then we jumped to 25, and we jumped to 62. So we start off growing slowly, and we grow faster and faster and faster. But if you look the other direction, the same thing seems to be happening, except we seem to be going down. Notice, From -2 to -1 was a growth of 1 space, and from here it's a decline of 1 space. Between these two, it was a growth of 7. Between these two, it's a decline of 7. In fact, the rate at which we grow stays the same. The only thing that changes is the direction we're growing. This shape right here is a very common shape, and it's always created by this type of function. Notice this x cubed, that's our key feature. X cubed always gives us and here's another point, always gives us a cubic function. And the graphs of all cubic functions will always make a shape that's kind of like this. Now, sometimes they're going to be a little less steep and they're going to be really wide. Sometimes they're going to be really steep and go almost straight up. Sometimes they might be completely flipped over. Sometimes they might be moved way off to the right, and other times they might be moved way off to the left or way up. This curve can appear a lot of different places and can be stretched in a lot of different ways. But a cubic function will always make this shape. Knowing that, we can begin to predict what this will look like without having to go to the trouble of graphing a whole table of values. We can cut this down actually quite a bit. Before we talk about that, let's talk about the domain. Remember, the domain is where this graph goes right and left. If I start here in the middle and go to the right, it looks like it goes to the right forever. It's very, very steep, but it's still going to the right. So if I were to pick a number like 10 and plug it in, 10 cubed is 1,000, minus 2 is 998. 10 will work. If I put in 100, 100 cubed is what? A 1 with 6 zeros after it, minus 2? I'm not going to take the time to compute that, but it does work. This is going to go forever to the right. Likewise, if I look at where this goes to the left, it's going to go forever as well. If I were to put in a -10, -10 cubed is -1,000 minus 2 is -1,002. If I put in -1,000, I'm going to get, what, -1 with 9 zeros minus 2. No matter what number I stick in, it's always going to work. So for a cubic function, the domain is all real numbers. No matter what value I stick in, something will come out. Let's talk about the range. The range is where does this go up and down. The range is what values come out of my function. Well, let's look and see. If I put in a 1, I got -1. If I put in a 2, I got a 6. If I put in a 3, we said we got a 25. Connecting the dots shows that everything in between also works, and the arrow shows that this is going to keep going up forever. If I go the other direction, I come back through the 0, -2, and then I come down, notice that it continues going down forever. If it goes up and down forever, your range is everything. No matter what number I give you as an output, there is some number we can stick in to create it. That's your range, all real numbers. And this is going to be true for every cubic function. It's nice to know that ahead of time, and we'll talk more about that in a future video. Lastly, there are 2 features I want to make sure that you see in this graph. Do you see anything of interest or of value? Notice it does not have a line of symmetry. There's nowhere I could draw a vertical or a horizontal line where I could use it like a mirror, as I did in the absolute value functions or in the quadratic functions. But it does have a vertex where it changes its behavior. This vertex, you'll notice, if I go to the right, it goes up 1, up 7, up 19. And if I go to the left, it goes down 1, down 7, down 19. At this point right here, my graph stops what it's doing and begins curving the other direction. That's what makes it a vertex, and that's the coordinate 0, -2. One more key feature is that this has rotational symmetry. Even though I can't draw a line where one side reflects to make the other, if I were to take this and put a pin right here in the middle, and I were to treat these 2 arms, these 2 sides of the graph, like propellers on an airplane, I could actually take this dot and spin it around, and it would match this dot. and this dot would spin around and match this dot. And this dot would spin around and match this dot, and this dot would spin around and match this dot. I can spin this graph and make this side go down here and this side go up at the top, and it would still match. Very important. Why is that? Well, let me erase all of this real quick. Because when I'm graphing, if I can graph this side of the graph, and I realize this is up 1 over 1, without having to plot points, I can figure out the other side is down 1, backward 1. Instead of going up 7 over 1, I could then go down 7, backwards 1. I can use one side of this to figure out the other side without having to make my table quite as large. Very, very helpful, very, very useful in trying to do these things quickly. Now, there's a lot more we could say about this, but I don't want this video to get overlong, and we are going to revisit this again in the near future and learn how these tools can help us go faster and faster. As always, make sure you come back to watch our next video. We've only made it through 4 of the 7 types of functions that we need to be familiar with before we can really have a conversation about how all these pieces fit together. So please make sure you hit that notification button so you'll know that when we get those next videos up. Make sure you like and subscribe. Leave us a comment in the comment section. And as always, take care of yourselves. Have a great day. We'll see you later. Bye-bye.